A black hole seems to be the end of everything, a place where light disappears, where matter loses its usual form, where time ceases to behave calmly, and space becomes a trap with no visible way out. But the deepest mystery of black holes is not only what they absorb. The real mystery is that one of the most powerful sources of energy in the universe may be lurking around them. Not the ordinary energy of stars, not chemical fuels, not the faint glow of distant planets, but the energy of space, rotation, gravity, and the very structure of time. At first glance, this sounds almost impossible. A black hole does not emit light from beyond the event horizon, and everything that crosses this boundary does not come back. But the energy of a black hole does not necessarily have to be extracted from its inner darkness. The main source may not be inside the horizon, but around it, in a region where gravity becomes so powerful that space itself begins to rotate with the black hole. Rotating black holes have a zone where rest becomes impossible.
You can't just hang still there relative to the distant universe. Space is drawn into circular motion, and everything that falls into this region is forced to participate in rotation. This area is called the ergosphere, and it is this area that makes the black hole not only a space trap, but also a possible machine for extracting energy. A black hole is born when the mass is compressed to a limit at which no known pressure can keep it from further gravitational collapse. In stellar black holes, this end is associated with the death of massive stars. The core loses stability, the outer layers can be thrown into space, and the central part falls into its own gravity. The space around it bends so much that an event horizon appears, a boundary beyond which all paths lead deeper. But if the original mass rotated, then the resulting black hole retains its rotation, and this rotation can be monstrous. It is not like the movement of a solid body. A black hole has no surface in the usual sense. The geometry itself revolves around it, and this creates one of the most extreme physical processes in the universe.
The energy of a rotating black hole is not contained in flames, not in matter, not in habitual fuel. It is contained in its angular momentum. The faster a black hole rotates, the more energy can theoretically be extracted from its gravitational field. In the extreme case, a rotating black hole can contain a huge fraction of its mass in the form of rotational energy. This does not mean that the entire mass can be converted into usable energy. But even a small part of such energy exceeds everything that ordinary sources provide. The mass of a black hole itself is a gigantic store of energy, because mass and energy are fundamentally related. The question is not whether there is a lot of energy there. The question is whether there is a way to take it away without disappearing with it. The most famous theoretical path is related to the ergosphere. In this area, the object can still get out if it has not crossed the event horizon. But the energy of the object there behaves unusually. Under certain conditions, some matter can fall on a trajectory with negative energy relative to the outer universe and fall into a black hole. The other part can fly out with more energy than it had before. From the outside, it would look as if the black hole had given off some of its rotation. It slowed down a little and an energy gain came out. This is not magic or a violation of the law of conservation of energy. The lost energy is taken from the rotation of the black hole itself.
This process shows why black holes cannot be considered only absolute eaters. The event horizon does not really release anything back, but the area around it can be an arena for energy exchange. If a black hole is rotating, it contains an available external supply that is not completely hidden below the horizon. The ergosphere becomes a cosmic zone where the line between falling and extracting energy becomes incredibly thin. Any mistake there would mean the loss of the substance forever,
but the right trajectory could turn a fall into a win. There is another, more natural way to release energy, the accretion disk. When gas, dust, or decayed matter fall toward a black hole, they rarely fall upright. Normally, the substance twists, forms a disk, and heats up to extreme temperatures. Friction, magnetic fields, shocks, and gravitational acceleration turn some of the mass into radiation. That's why some black holes may be some of the brightest objects in the universe, even though they don't shine on their own. It is not the event horizon that shines. Matter that has not yet crossed the last border glows.
Accretion around a black hole can be much more efficient than conventional nuclear burning in stars. In stars, only a small fraction of the mass is converted into energy through thermonuclear reactions. In the vicinity of a black hole, the efficiency can be much higher, especially if the black hole is spinning rapidly. Matter manages to get closer to the horizon, lose more gravitational energy, and release it in the form of light, heat, X-rays, particles, and powerful streams. In the most extreme systems, energy is released into space in the form of narrow jets that can stretch over vast distances and carry colossal power. But the accretion disk is not a perfect powerhouse. It is a chaos of plasma, radiation, magnetic storms, and gravitational hell. The temperature in it can reach millions of degrees. Matter does not lie there still, does not flow evenly, does not obey simple schemes. It tears, contracts, heats up, collides, and emits deadly radiation. Any technology near such a disk would have to withstand conditions that are far harsher than conventional spacecraft face. Even if the energy is huge, approaching and controlling it is a completely different task. The main temptation of black holes as a source of energy is that they offer not just power, but the depth of physical potential. A star radiates energy while reactions are taking place in its core. The planet stores chemical, thermal, or radioactive reserves, and a rotating black hole stores energy in the very geometry of space-time. The closer you get to it, the stronger the difference between the weak gravity of ordinary space and the extreme gravity of a compact object. There, each kilogram of matter can release much more energy than in normal processes. If civilization is ever able to work with such conditions, black holes could become energy centers of incredible scale. A small black hole, if properly controlled, could be a compact source of energy. The supermassive black hole at the center of the galaxy could be a natural gravitational engine for processes of enormous size. But there is an abyss between theory and actual energy production. It is necessary not only to fly to the black hole, but also to survive next to it, stabilize equipment, transfer energy, avoid tidal forces, radiation, plasma flows, and unpredictable accretion bursts.
Tidal forces are one of the main dangers. The gravity of a black hole changes with distance. If the object is too close, the near part stretches more strongly than the far part. This stretches and destroys matter. In small black holes, such forces near the horizon can be monstrous. Supermassive black holes have a much larger horizon, and tidal forces at the boundary itself may be milder, but that doesn't make the region safe. Magnetic fields, high-energy radiation, plasma, and unstable orbits remain there. A black hole does not have to tear an object apart immediately. It can kill it by radiation, overheating, particle collisions, or loss of orbital stability. The most unusual feature of a rotating black hole is the connection between energy and the direction of motion. In ordinary space, motion against rotation or rotation affects velocity and orbit, but does not change the very meaning of energy so profoundly. In the ergosphere, this becomes fundamental. Space is so caught up in rotation that trajectories that seem strange from the outside can make real energetic sense. Negative energy inside the ergosphere does not mean negative mass in the usual sense. This means that in a relatively distant universe, the falling part takes away part of the black hole's rotational reserve. After that, the black hole becomes slightly less rotating, and the outer part receives excess energy.
In real nature, similar ideas manifest themselves through magnetic fields. Around a rotating black hole, there may be plasma permeated with powerful magnetic lines. The rotation of the black hole and the surrounding plasma is capable of spinning these fields, converting gravitational energy and rotational energy into particle flows. This is how relativistic jets can appear, narrow emissions where matter and energy move at almost the speed of light. Such jets show that black holes are capable of not only absorbing, but also launching gigantic energy structures. They do not eject material from inside the horizon. They feed on the processes around it. There's an important truth hidden in this. A black hole itself isn't a convenient battery. It is more of an extreme natural machine that requires the right environment. Without falling matter and magnetic fields, it can be almost invisible. With an accretion disk, it turns into an engine of enormous power. With a fast spin, it becomes even more interesting. Energy does not appear out of the void. It comes from the mass of the falling matter, from the gravitational potential, and from the rotation of the black hole itself.
The future of energy extraction from black holes is most often associated not with giant natural objects, but with hypothetical small black holes. If it were possible to create or capture a microscopic black hole and hold it, it could radiate energy through a quantum evaporation process. The smaller the black hole, the stronger the radiation. But here begins an even more difficult part. A black hole that was too small would evaporate too quickly and dangerously. Too large would produce little radiation and would be extremely difficult to move and control. You need to get into a narrow mass range where the energy is high, but the object is quite durable. At the moment, this is not an engineering project, but a distant physical hypothesis. Quantum radiation from black holes makes the topic even more mysterious. In classical physics, the event horizon does not release anything, but quantum effects near the horizon indicate that the black hole may gradually lose mass by radiating energy. For large black holes, this process is so weak that it is almost imperceptible against the background of cosmic radiation. For small black holes, it could be powerful. This turns the microscopic black hole into a strange energy object. The smaller it gets, the faster it loses mass and the stronger it radiates. An extreme flare is possible at the end of such a process, but the exact details remain among the deepest questions of physics. To be honest, today, humanity does not know how to extract energy from black holes. There is no ready-made technology. There is no working project. There is no real way to build a power plant on the ergosphere. There are physical ideas, calculations, and observations of natural processes around black holes. They show that the energy there is really huge, and that some of this energy can theoretically be extracted. But between physically possible and technically feasible, there is a distance equal to entire epochs of civilization development. However, that is why the theme is so strong. Black holes are on the border between horror and possibility. They destroy familiar matter, but at the same time open up access to energies that are superior to ordinary stellar processes. They hide the center behind the event horizon, but leave an area outside where rotation can theoretically be used. They seem to be a void, but around them, the brightest accretion disks and the most powerful jets are born. They look like the end, but the physics around them constantly hints at a hidden energy order.
If a future civilization ever reaches a level where stellar energy is scarce, black holes could be the next step. Not because they are safe, not because they are simple, but because they contain energy in its deepest form. The star gives off energy gradually through thermonuclear combustion. A black hole stores rotational energy in curved space. Its accretion disk converts falling matter into radiation with tremendous efficiency. Its magnetic fields can trigger streams that cross intergalactic space. All this makes a black hole not just an object of darkness, but one of the most powerful natural engines of the universe. But the price of such energy is almost absolute. To use a black hole, you need to get closer to a place where weak mistakes become fatal. You need to control the orbits near the event horizon. It is necessary to understand plasma and extreme magnetic fields. You need to protect yourself from radiation that can destroy any ordinary structure. It is necessary to transmit energy over huge distances. It is necessary not to lose control over the system, where the fall inside becomes irreversible. Such a power plant will not look like an ordinary plant. It will be a struggle with the very geometry of space.
The illusion of complete control remains especially dangerous. A black hole does not have a solid surface that can be bypassed, anchored, or used as a support. There is no stable, familiar environment next to it. Even orbits have a limit. Too close to a non-rotating black hole, circular orbits become impossible. With rotating black holes, the situation is more complicated. The direction of rotation changes the permissible trajectories, the inner regions become even stranger, and the energy of motion is associated with the geometry itself. Any energy system there must be calculated with such accuracy where ordinary mistakes are unacceptable. The question of black holes as a source of energy leads to a deeper topic, the level of future civilization. As long as energy is taken from chemical fuels, atomic reactions, starlight, and the movement of water or wind, civilization remains tied to the planet's mild conditions. When energy is taken directly from the star, the scale increases. But a black hole opens up an even more radical level. It allows us to think not just about collecting light, but about extracting energy from the gravitational fall and rotation of space. This is no longer the energy of the surface of the planets. This is the energy of the ultimate states of matter.
Possible black hole energy can take several forms. The most realistic in the long run is the use of accretion. It is necessary to direct the substance to the controlled disk and collect the radiation. Such a process could produce enormous power if a steady flow of matter could be maintained. A more difficult way is to extract rotational energy through the ergosphere or magnetic mechanisms. There, the task is even more difficult, but potentially deeper, because it is not only the falling matter that is used, but the rotation of the black hole itself. The most fantastic path is a controllable small black hole that radiates through quantum effects. But this option requires capabilities that are not available now, even in the initial engineering form. Supermassive black holes at the centers of galaxies are especially interesting for their scale. Their mass can be millions and billions of times that of the Sun. Their gravitational influence shapes the motion of stars and gas in the central regions of galaxies. When such objects are actively nourished, they can transform the surroundings into powerful energy systems. But it would be almost impossible for a planet-level civilization to use such a system. The distances are too great, the processes are too strong, the power is too great, the environment is too difficult to manage. There is energy there, but it belongs to the scale of galaxies, not ordinary machines. Stellar black holes are smaller, but closer to the idea of a compact power plant. Their mass can be several or tens of times the mass of the Sun. They have a smaller horizon and stronger tidal effects near it. The accretion disks around them can be bright sources of X-rays. But it is their compactness that makes them more dangerous. Approaching such a black hole requires precision and protection from the destructive gradients of gravity. The energy there is concentrated in a smaller volume, and this increases the risk. Small hypothetical black holes seem to be the most convenient only on paper. In reality, they are the ones who create the most pressing questions. How to create them? How to keep it? How to give them the substance? How to prevent a dangerous loss of control? How to extract radiation if it can be too harsh and destructive? How to adjust the power? How to make the process stable? These questions do not have a ready-made answer. Therefore, the honest conclusion is that black holes may be one of the most powerful sources of energy in physical theory, but they are not yet a practical source of energy.
This is the hidden power of the theme. It's not about fantasy, where a black hole just becomes a battery. It is about a real physical conflict between possibility and impossibility. On the one hand, black holes do have huge energy resources. Accretion is able to release energy extremely efficiently. The rotation of a black hole could theoretically give up some of its energy through the ergosphere and magnetic processes. The quantum evaporation of small black holes opens up another avenue. On the other hand, none of these paths are available technology. Everything requires a level of control over matter, radiation, gravity, and space that does not yet exist. The biggest mystery remains where the line is between natural power and managed energy. The universe is already showing that black holes are capable of releasing incredible power through their surroundings. Active galactic nuclei, quasars, X-ray binary systems, and relativistic jets prove that near black holes, energy can be released on scales that are beyond conventional imagination. But nature does it chaotically, destructively, and not for the convenience of life. Future technology would have to turn this chaos into a controlled flow. This is much more difficult than just finding a source of energy.
If a black hole becomes an energy source, it will change the understanding of the cosmic future. Civilization will no longer be completely dependent on the stars. It will be able to use objects that will survive many stellar epochs. Black holes can exist for an incredibly long time. Supermassive black holes can persist for times that exceed the lifetime of ordinary stars. In the distant future, when many stars go out, it is black holes that may remain among the last large energy objects in the universe. Then the question will change. Can black holes become a source of energy? And what will be left when the starlight begins to disappear? In the very distant future, the universe will become colder and darker. Star formation will weaken. There will be less free gas. Many stars will go out or turn into compact remnants. In such a picture, black holes become not only a symbol of the end, but also the last stores of mass and energy. Their evaporation through quantum processes can last for an incredibly long time. Large black holes will lose mass extremely slowly. For future intelligence, if it can ever exist in such eras, black holes could be the last fires of the universe. But this is no longer the energy of the near future. This is the energy of cosmic times, where the very concepts of life, matter, and structure can become different.
Black holes also make you reconsider the meaning of energy. In conventional engineering, energy is something that can be transferred, stored, transformed, and used. Near a black hole, energy is associated with the observer, trajectory, gravitational field, and horizon. What looks like a loss of mass or a slowdown in rotation from the outside is due to deep geometry near the horizon. Energy ceases to be a simple quantity. It becomes part of the space-time arrangement. That is why black holes are so important, not only as objects, but also as a test for all of physics. The question of extracting energy from a black hole inevitably leads to unsolved mysteries. What actually happens to information when matter crosses the event horizon? How exactly do gravity and quantum processes connect?
How does the final stage of black hole evaporation work? Is it possible to fully describe the internal structure of a rotating black hole? Are there small primordial black holes in nature? Could dark matter be associated with such objects? How do magnetic fields near the horizon create such powerful jets? Why are some black holes active while others are almost silent? These questions are not just details. It depends on them how deep such objects can ever be used. A black hole as an energy source is not only a topic about the future. This is a topic about power over limits, over the fall of matter, over the rotation of space, over the light that hasn't disappeared yet, over the border beyond which there is no return. There is a cold beauty to such an idea. The darkest object can become the most powerful source, not because it shines, but because everything around it is forced to give energy when it falls. Not because it is generous, but because the laws of physics allow you to extract some of the energy to the last limit. If one day a controlled energy system appears next to a black hole, it will not look like a conventional technology. It will be a structure working on the edge of gravitational silence. It will collect radiation from the accretion disk, control plasma flows, use magnetic fields, direct matter along precise trajectories, and extract energy from rotation. It will exist where any mistake disappears beyond the event horizon. Such a system will become more than just a machine. It will be proof that the mind is able to interact with the deepest structures of the universe.
But this path is still very far away. Today, black holes remain not sources of energy for civilization, but natural laboratories of ultimate physics. They show how much energy is hidden in gravity. They prove that the fall of matter can be more powerful than many habitual processes. They reveal that the rotation of space-time is not an abstraction, but can participate in the actual transfer of energy. They remind us that the universe stores resources not only in stars and planets, but also in areas where the usual physical intuition ceases to work. The most honest answer is that black holes could be one of the ultimate energy sources in theory, but not in the near technological future. They are too dangerous, too complex, too far from the capabilities of today's civilization. However, physics already shows that the energy around them is real, enormous, and partially available through processes that do not violate the laws of nature. This is the main dramatic meaning. A black hole does not only devour energy. Under the right conditions, it can give it outward, turning its own rotation, falling matter, and magnetic fields into power on a cosmic scale.
And the deeper this idea is revealed, the more the image of a black hole changes. It ceases to be just a bottomless shadow. It becomes the final exam for any civilization that wants to go beyond stellar energy. To use sunlight means to live off the star. To use a black hole is to work with the very boundary of space and time. Such a source will not forgive weakness, but its potential is so great that in the distant future it can determine which civilizations will survive the extinction of starlight. Perhaps the darkest regions of the universe will one day be not the end of the road, but the beginning of a new energy age. Not bright, not safe, not close, but grandiose. Where the light no longer returns, there is still rotation. Where matter disappears, flows of energy are still born. Where the event horizon sets the last boundary, there is space around it in which the universe still allows the fall to win. A black hole does not give away its power easily, But if there is ever a technology that can approach its edge and not die, the most feared object in space could become the most expensive and powerful source of energy ever available.